So in this lecture, we are talking about the geometry of solution for semi-linear equation. So we know that the semi-linear equation is considered as p of xy zx plus q of xy zy is equal to r of xyz. I will call this equation as the equation number 1. So consider the semi-linear equation in this form. Where this P, Q and R are continuously different. And both this P square or P and Q are simultaneously non-zero. That means we can say that P square plus Q square is not equal to 0. That means P and Q, both of them are not 0 simultaneously. The expression which is given in the left hand side of this equation number 1 is actually a directional derivative. So we know that the gradient of z, if the z is a function of two variable, dot product with pq will be written as, that is, del z by del x, del z by del y into dot product with pq, will gives you exactly the same thing which we have in the left hand side. So what we can say that the expression on the left hand side of this equation 1 is the directional derivative of z in the direction of pq at the point xy. So now let us consider a one parameter family of curves in xy defined by the ordinary differential equation dy by dx is equal to q of xy upon p of xy. So we'll consider this is first order differential equation, or the system of OD, that is ordinary differential equations, that is dx by dt is equal to p of xy and dy by dt is equal to q of xy. So either you consider this ordinary differential equation, or you can consider a system of ordinary differential like this. Now we'll note that here this curve, whatever the solution of that curve, so this curves have the property that along them z of xy will satisfy the ordinary differential equation dz by dx. So z is a function of two variables x and y. If you want to calculate dz by dx with respect to x, where y is an independent variable, where y is a dependent variable on x, then we'll have, so y is also a function of x. That is the thing we have. So to take the derivative of z with respect to x, we'll have del z by del x into dx by dx plus del z by del y into dy by dx. But dx by dx will be 1, so it is zx plus zy dy by dx. But dy by dx we have assumed that is q by p. So that's why this will be have it is zx plus zy into q by p. If you take the LCM, then you will have p into zx plus q into zy upon p. If you consider this way, that is a system of linear equations, then your z is a function of t, or I can say you will have dz by dt. So here z is a function of x and y both of them are function of t. So it is del z by del x into dx by dt plus del z by del y into dy by dt. This is the things we got. But dx by dt we have assumed that is px. So that's nothing but the p of xy zx dy by dt we have assumed it as qx, so it is dy qxy into zx we have zy. So the one parameter family of the curves c lambda 0 defined by the equations, the two equations that we have. The first one is, let's say this is equation number 2, and the last one we have got, this is equation number 3. By equation 2 are called, so whatever the solution for that system of linear equation that we have here, they are called the characteristic curves, are called the characteristic curves. Of the partial differential equation p.d.e zx plus q zy is equal to r. That is the semi-linear equation that we have. So it is whatever the solution for those equations which we have in the 2, it's called characteristic curve. Let this x0 y0 be the point in xy plane. So let us consider this x0 y0 is a point in xy plane, and the existence and uniqueness of the initial value problem that we have onto the ordinary differential equation will gives you there is a unique solution, or I can say unique characteristic curve is possible. What I can say, by the existence and uniqueness of the solution of the initial value problem for ordinary differential equation, that is ODE, the equation 2 will define a unique characteristic curves. So whatever the solution is, that it is a unique characteristic curve, that is x of t is equal to x of x0 y0 t, and y of t is equal to y of y0 y0 t, sorry, x0 y0 t. And I'll call this as equation number 4, such that this x of 0 is equal to x0, that is the initial condition that we have, y of 0 is equal to y0. Suppose now we have assigned the values at 0 for z of xy at x0 y0. So suppose we assign a value z0 for z of xy at x0 y0, then this equation 4 determines the unique solution as then the equation 4 determine a unique solution z as z is equal to z of x0 y0 t, and that is the characteristic curve where z of x0 y0 0 is z0. That is the uniquely determined along the curve or characteristic curve passing through the point x0 y0, and this value we assign for the value z at x0 y0. So this is, so that is xy, z of xy is continuously determined, sorry, uniquely determined along the whole characteristic passing through x0 y0 if we assign a value for z at x0 y0. Hence if z of xy is known on the curve gamma 0 in xy plane, and if this curve is such that it is intersect the one parameter family of characteristic curves C lambda 0, we can determine z of xy uniquely in the region covered by C lambda 0. And we should note that this lambda 0 which we have obtained here is arbitrary. Chosen is arbitrary, and we can deal with this point later on. Okay, so let us see one of the examples based on this. So this is the example. Solve x zy minus y zx is equal to z with initial condition z of x0, well, z of x comma 0 is equal to f of x if x is greater than or equal to 0. So this is the initial condition is given, and we need to find out what will be the solution for this one. So first you should compare this equation with the given equation. So comparing with p zx plus q zy is equal to r, we get p equal to, you just observe the coefficient of zx is minus y. So the value of p is minus y, value of q it is x, and r is z. So now we need to define a characteristic curve as per our theory. We need to define a characteristic curve in this two system of linear equation. That is, either you can take this dy by dx is equal to q by p. Any one of them you can take one, and you can proceed for this example. So what we'll do, we'll consider the characteristic curve are given by the equation dy by dx is equal to minus, as per the formula it is, it is q by p, but q is nothing but the x, p is minus y, so it is minus x by y. Now we need to find out what will be the solution for this, and it is easy to calculate. Since the equation is dy by dx is equal to minus x by y, you can use the separable variable method to obtain the solution for that. That is y dy is equal to minus x dx. So that's why it is y square by 2 plus x square by 2 is equal to c square by 2, where c is a constant, and that you can adjust constant by this manner. So finally you will have x square plus y square is equal to c square. And this is the curve which represent, we know it is represent the circle. We can see in the xy plane. If you can see in the xyz plane, then it is a cylinder. Now along the curve, z satisfies the ordinary differential equation. Along the curve, z satisfies the ordinary differential equation, that is dz by dx is equal to as per the formula, which what we have is z is a function of xy and y is a function of x. So you have del z by del x into dx by dx plus del z by del y into dy by dx. So del z by del x so that we can, dx by dx is 1, and del z by del y is dy by dx we already have. So this will gives me del z by del x plus del z by del y into dy by dx, and that will gives me zx plus zy into dy by dx. We already calculated here, that is x by minus y, so that's why it is minus x by y. If you take the LCM for this one, that will gives me y del zx minus x zy upon y. But as per the given differential equation, that is x zy minus y zx is a z. So that's why this is z by y. Okay, y zx. Sorry, it should not. It is not coming. What we have, it is, sorry, it is x minus x by y is there. Here it is minus, not y x by y. So it is, yeah, it is x by y itself. So it is x by y. It is fine, x by y. But the equation is given is x zy. The first value is this, and the second value, so it is minus of this. The equation is given is this: x zy minus y zx is equal to z. So this is the equation. So that means y zx minus x zy is minus z. So that's why it is minus z by y. But from the previous situation, we can obtain the value of y, that is the square root of c square minus x square. I am considering the positive square root. So hence we got dz by dx is equal to minus z by y. dz by dx is equal to minus z by y, and the value of y we can obtain from the given situation is square root of c square minus x square. Now again use the separable variable method to obtain the solution for this one. So it is dz by z is equal to dx by square root of c square minus x square. If I take the integration both sides, this is ln of z is equal to integration of 1 upon c square minus x square. Square root is there. So we know that it is the integration is sine inverse of x by c. So we know that the formula under root of a square minus x square dx, it is sine inverse of x by a. 1 upon c is here, 1 upon c, so it is 1 upon a sine inverse of x by a. This is the formula. Is this the 1 upon c is coming? I don't remember. Anyone know the formula of integration? I think so. 1 upon x is there or not? I don't know. So this 1 upon a is not there. So it's like this, plus some constant is there. So that constant, I'm just saying that it is ln of some constant, let's say k. So where k is arbitrary constant may depend on c. It may depend on c because it is a one parameter family. So this is gives me z by k is equal to e power sine inverse of minus x by c. This minus is already there. So here is minus is there. So z is equal to k into e power minus sine inverse of x by c. And this k is a function of c. So that's why it is z is equal to k of we have already got the value of c. From this, it is a x square plus y square. Okay, so this is a function of x square plus y square into e power minus sine inverse of x by c. Now we need to calculate what will be this function k and the value of c here. What will be this k function? For that, we have given this initial condition, that is f of xz or f of x0 is fx, which is given to us. So I'll substitute now y equal to 0 into this expression. So putting y equal to 0, we get z of x0 is equal to k into x square e power minus, if I put here initial conditions, that is sine inverse of, because the value of c is x square plus y square, c square. So if I can say put y equal to 0, this is x square and square root will be x. So it is actually sine inverse of 1. Sine inverse of 1 will gives me pi by 2. So that will gives me k x square e power minus pi by 2. And this value is fx. So we'll have fx is equal to this much. What is this? We got it is fx is equal to k x square e power minus pi by 2. Ultimately, I want to calculate what is k function. So the k x square is e power pi by 2 into fx. So k of fx, so sorry, k of x, that is a square is there, then square root will be here. So if it is x is there, then it will be a square root of that, f square root of x. So this is our required function k, and hence the solution, the required solution is z of xy is equal to, that is this, z is equal to k, the value k of x square plus y square. But k of x, according to this, it is e power pi by 2. So it is e power pi by 2 f of square root of x square plus y square e power minus sine inverse of x by c. It is our answer. That is the value we have, e power minus sine. So this is our final answer that we have. Now we'll discuss. So what we have discussed here is geometry of semi-linear equations. Now we'll discuss the geometry of quasi-linear equations.